All right. Hey everybody, I'm going to be working through problem 5, parts B, C, and D today. If you forgot what 5A was, it's the reaction of this alkene with HCl to make both a minor and major product based on some regioselectivity differences. Part B is asking us to draw the difference in the reaction coordinate diagrams between the major and minor products. And so if we were going to start thinking about this problem, right, the first thing I would think about is the intermediate. We know that the reaction of an alkene with HCl goes through a carbocation intermediate, so we know this right here has to be the carbocation. So it might be a good idea to start by looking at the difference in the carbocations between the minor and major products. We know that the Cl minus will add where the carbocation is, so the carbocation must be here for the minor product. I'll draw minor. And that's a primary carbocation, versus the major product, which is right here. That's a tertiary, that's the major. Now we know that tertiary carbocations are more stable than secondary, which are even more stable than primary due to hyperconjugation. So we know that the intermediate of the minor product must be higher in energy compared to the major product. Now, if here are our reactants and here are our products, the reactants will be the exact same energy because it's the same reactant, and the products will be roughly pretty similar. So what's really going to be different is in this middle. Since the transition state is pretty close in energy to the intermediate, we know it's going to resemble the intermediate at least to some degree. So if there is an energy barrier at the intermediate, there must also be an increased energy barrier at the transition state as well. Part of this is because as we're moving towards that carbocation, we're creating a less stable carbocation in the minor product as compared to the major product, which means there must be more energy associated with that. So if I were to draw the minor product in red compared to the major product in black, I would start here with the same energy at the reactants. Sorry, that was kind of bad. And then I would draw a difference in their transition states here, a difference in their intermediates, and then also a difference in their second transition states. And then I would come back down and have very similar energies at the product level. We're not asking you to differentiate which one of these might be more stable based on the products, but based on the carbocation in transition states, we know that the minor product must go through a much larger energy barrier compared to the major product. Now, for C, we asked for the transition state number 2 of the major product. So there are 2 transition states. The transition states, if you remember, are these 2 humps right here. The highest energy points in the reaction. This is where bonds are half formed and half broken. And we can't isolate this as we could with an intermediate. So if we were to look at transition state number 2, that's this transition state right here, which means we've already formed a carbocation. This must mean that this transition state is the addition of the chloride ion onto the carbocation. So the first thing I'll draw is my base structure here. And I'm not going to draw a full carbocation because in the transition state, we have partial charges. So what I'll do instead is I'll put a partial positive here to indicate that's where the partial positive is on that carbon. And then I know I have a half-formed bond with a chloride, which is a partial negative. This would be the example of the transition state. And if you compare this to where our intermediate was, we had a fully formed carbocation and a Cl minus anion. And through this mechanism, we show an attack of that carbocation from the Cl anion. And the transition state, this is the halfway point where our chlorine-carbon bond hasn't yet formed, but is beginning to. That's why I show partial positive and partial negative charges instead of full charges. And lastly, in part D, we talk about HCl versus HBr in terms of the reaction rate. So going back up to the reaction, let's take the same alkene and react it with HBr instead? Would that be faster, slower, or not change the rate? Well, since the alkene stays the same in both reactions, we know that that is not influencing this reaction rate. So we have to look at the differences between HCl and HBr. Taking this back all the way to like unit 1, when we were first talking about electronegativity and size differences, I would draw, to think about this, I'll draw an example of H bonded to a Cl like this. We know that the dipole points this way, and that hydrogen has a partial positive and Cl has a partial negative. But if we compare this to HBr, which also has a partial negative, and H has a partial positive, the difference here is that since Br is so much larger, this HBr bond is significantly weaker compared to the HCl bond. This is also why we see HBr tends to be a stronger acid as compared to HCl, and why the trend follows in terms of acidity. Hydrogen iodide is more than HBr, more than HCl, which is more than HF. The HX bond, where X is a halogen, gets weaker as you increase the size of the halogen. So if this bond gets weaker, then the hydrogen becomes easier to pull off as it goes. We also know that based on this first step to make this transition state, where the alkene actually attacks the hydrogen, is the rate limiting step. That has the largest energy barrier, and that's where we make the carbocation. So if that hydrogen is easier to pull off or easier to react with, then that rate limiting step has less of an energy barrier and thus must be faster. So the answer to this question is that if we used HBr instead of HCl, we know that the reaction rate, I shouldn't have erased, we know that the reaction rate must increase. And that's all. Thanks for watching.